The study of chemistry touches on almost every aspect of our environment and human life. It helps us understand why icebergs float, how to get the fizz in soda pop, and what gives fireworks their spectacular colors. Knowledge of chemistry is essential in biology, medicine, ecology, and even archaeology. It provides answers to one of the most basic questions that have puzzled us from the beginning of time. What makes up all the things in the world? This program will focus on atoms, the tiny units that are the fundamental building blocks of matter. The roots of the modern atomic theory can be traced back to Democritus, one of the ancient Greeks, but it was only a little over 100 years ago that the evidence was found to prove that atoms actually existed. In 1897, J.J. Thomson, a British physicist, found a tiny negatively charged particle that he called an electron. A few years later, Ernest Rutherford found evidence of the nucleus of atoms. With such painstaking research, a picture of atoms began to emerge. We now know that atoms are composed of protons, neutrons, and electrons. The nucleus comprises protons and neutrons. Each proton carries one fundamental unit of positive electrical charge. Neutrons have no charge. The electrons move about in the space around the nucleus. They carry a negative electrical charge. Positive and negative electrical charges attract each other, and it is that attraction that holds the atom together. The reason why it was so difficult to understand atoms is that they are so incredibly tiny. To give an idea of their size, about 50 million atoms of solid material lined up in a row would measure 1 centimeter, about the thickness of a single French fry. Atoms are tiny, but the different parts of an atom are even a fraction of that size. Compare the nucleus of an atom to the size of a marble at the starting line of a 100-meter track. The electron would be the size of a speck of sand halfway down the track. The rest of the atom is empty space. Although atoms are considered the smallest units of matter, research has shown that there are more than 100 different subatomic particles. However, for the purposes of chemistry, they have no immediate impact. Chemical behavior of matter can be understood simply in terms of protons, neutrons, and electrons. We have described the basic structure of atoms, but there are different types of atoms with different numbers of protons, electrons, and neutrons. They are called elements. The simplest element is hydrogen. It has 1 proton and 1 electron. Hydrogen is by far the most abundant element in the universe. Other elements have varying numbers of protons and neutrons. This oxygen atom has 8 protons and usually 8 neutrons. When it is electrically neutral, an oxygen atom also has 8 electrons. In total, there are 92 elements found naturally in the universe, and another 20 or more that have been created in laboratories. This periodic table is a list of all the elements. Every element has an atomic number, which is the number of protons that are found in the nucleus of the atom. Hydrogen has the atomic number of 1 and only has 1 proton. Iron is 26 and has 26 protons. Gold is 79 and uranium has the atomic number 92. For any element, the number of neutrons in the nucleus can vary from atom to atom. Atoms of an element with different numbers of neutrons are called isotopes of the element. For example, most carbon atoms have 6 protons and 6 neutrons. But carbon atoms frequently have 7 neutrons. This is called carbon-13. Carbon can also have 8 neutrons, carbon-14. The number of the isotope is determined by adding the number of protons and neutrons. The atomic mass of an atom is the total mass of all its protons, electrons, and neutrons. Scientists use the term mass rather than weight because it is a measure of the total quantity of an object's matter. In space, all objects are weightless, but they never lose their mass. Every element has a different atomic mass. The unit of measurement is defined as the atomic mass unit, or AMU. Chemists base the unit of measurement on the mass of the element carbon. A carbon atom was defined as having an atomic mass of 12 AMUs. Thus, 1 AMU is 1/12 of the mass of a carbon-12 atom, and is roughly equal to the mass of a proton or a neutron. But if you look at the periodic table, carbon does not have an atomic mass of 12. Any natural sample of an element contains certain percentages of isotopes, which have different mass values. On the periodic table, the value given for atomic mass is an average mass of the element including all isotopes. So the averaged atomic mass of carbon is 12.011. The atomic mass for all of the elements is determined in this way. The atomic mass of the different elements varies considerably. Hydrogen, with only 1 proton and 1 electron, is the lightest element with an average mass of 1.00794. As a general rule, the higher the atomic number of the element, the greater its mass. Isotopes of an element have a different mass, but essentially the same chemical properties. A neutral atom has an equal number of protons and electrons, giving it a neutral electrical charge. The positive electrical charges of the protons are balanced by the negative electrical charges of the electrons. But electrons have the ability to move from atom to atom, and this is what makes atoms bond together to produce compounds. When an atom loses or gains 1 or more electrons, it is called an ion. An ion with more electrons than protons is a negative ion because the atom takes on a negative charge. If it has fewer electrons than protons, the atom becomes a positive ion because it has a positive electrical charge. Look at a boron atom, which has the atomic number of 5. A neutral boron atom has 5 protons and 5 electrons. If it were to lose electrons, it would become a positively charged ion. A boron atom that has lost 3 electrons is written B3+. 3+ indicates it is a positive ion missing 3 electrons. If it were written B3-, it would indicate that it had 3 additional electrons. These symbols are called the oxidation numbers. This seems complicated, but is really quite a simple system developed by chemists to keep track of electrons. It's important to remember that the number of protons in the nucleus doesn't change. An atom is held together by the attraction between the positively charged protons in the nucleus and the negatively charged electrons. But particles with the same electrical charges repel each other. Why doesn't the nucleus fly apart? The reason it holds together is because of the strong nuclear force, one of the fundamental forces in the universe. This force operates between the protons and neutrons at extremely short distances. Elements with atomic numbers from 1 to 20 often have the same number of neutrons and protons, but elements beyond 20 need increasing numbers of neutrons to hold the protons together. Beyond atomic number 83, no number of neutrons is sufficient to indefinitely hold the element together. When there are changes in the nucleus of an element, it is called radioactive decay, or radiation. The original nucleus of an element decomposes to form a new nucleus, and thus a different element, releasing radiation in the process. There are three types of radiation. Alpha radiation consists of helium nuclei, 2 protons and 2 neutrons. Beta radiation consists of high-speed electrons. And gamma rays are a very energetic form of light, similar to X-rays. It is gamma rays that are particularly dangerous to humans and other life forms. Scientists and technicians must be very cautious when they come into contact with them. But nuclear reactions are an essential and natural part of our universe. The energy that we receive from the sun is the result of fusion that occurs when 2 hydrogen atoms fuse together at high temperatures. This releases energy that radiates outward as electromagnetic energy that we call sunlight. Scientists are working on harnessing fusion reactions because they are a means of producing a virtually limitless, clean supply of energy. We have even been able to create nuclear reactions ourselves by splitting apart the nuclei of unstable atoms such as uranium in a process called fission. This is the energy released in atomic bombs and nuclear reactors. In the early part of the 20th century, scientists found it difficult to understand the structure of atoms. Ernest Rutherford and his colleagues visualized them as negatively charged electrons circulating about a positively charged nucleus. A German physicist named Max Planck suggested that energy emitted or absorbed by an object could only be emitted or absorbed in discrete amounts or units. He called these units of energy quanta. Niels Bohr, a Danish physicist, visualized atoms much like our solar system, with the nucleus like a sun and the electrons orbiting it like planets. This is called the planetary model. He then applied Planck's idea of quanta to the behavior of the electrons surrounding the nucleus. He suggested that electrons' orbits depended on their amounts of energy. When an electron absorbs energy, it jumps from an orbit close to the nucleus to one further away. When an electron moves closer to the nucleus, it emits energy. In both cases, the energy is only in discrete quantities. Louis de Broglie, a French physicist, proposed that electrons were not only particles, but also a form of energy that acted in a wave-like manner. But the more evidence that was gathered, the more scientists came to understand that atoms were not like the solar system at all, because the electrons did not circle the nucleus in regular orbits. In one of the most significant developments, in 1927, Werner Heisenberg, a German physicist, showed that it was impossible to determine the precise location and velocity of an electron at the same time. All that could be done was to describe the probability of the location of electrons. This has come to be called the uncertainty principle. All of these ideas have come together into what is now called quantum theory, or quantum mechanics, one of the most important scientific advances of the 20th century. The uncertainty principle holds that it is impossible to know the position and velocity of electrons at the same time. All we can do is describe the probability that an electron might be found within a certain region. However, electrons with a given energy follow certain patterns around the nucleus. These are called atomic orbitals. Chemists picture the orbitals like clouds that are dense in areas where the electron is more likely to be, and less dense in others where there is less probability of it being found. Each atomic orbital may be described by a set of 4 quantum numbers. The principal quantum number is called n. As n increases in value, the atomic orbitals become larger in size, and the electrons are found further away from the nucleus. As atomic numbers of elements increase, they have electrons in these larger orbitals, and therefore the size of the atom increases. Orbitals of lower principal quantum number have lower energy. The electrons first fill up the orbitals of lower energy before orbitals of higher energy. The second quantum number, L, refers to the shape of the orbital. There are 4 important shapes, each with a slightly different energy. All S-shaped orbitals are spherical. P are dumbbell-shaped. And the D and F orbital shapes are more complicated, as shown in these drawings. The third quantum number refers to the orientation of the orbital. This refers only to the P, D, and F-shaped orbitals. And finally, the fourth quantum number refers to the spin of the electron. An electron can be thought of as spinning on its axis in 2 possible directions. This means an orbital can only accommodate 2 electrons, each spinning in opposite directions. So, the energy of an electron orbital is described by both the principal quantum number n and the second quantum number L together. As n increases, there is more than one orbital shape. For example, where n is equal to 2, there are s and p-shaped orbitals. S orbitals have lower energy than p orbitals and fill first. At n equals 3, d orbitals with higher energies than p fill last. This diagram shows how the orbitals of the elements from 1 to 10 fill with electrons, filling the orbitals of lowest energy first. The p orbitals take 1 electron each, and after this, pairing begins. This is repeated with all of the elements. It is called Hund's rule of maximum multiplicity. Look at oxygen, for example, element 8. A neutral oxygen atom has 8 electrons. The 2 in the first energy level are in the s orbital. In the second energy level, 2 are in an s orbital, and then as the p orbitals are filled, 1 electron goes into each of the p orbitals, and the last electron pairs with p1. The electron configurations of atoms have a direct relationship in how they interact with each other to create molecules and compounds and all matter in the universe. With an understanding of the structure of atoms and the behavior of electrons, it is possible to predict with great accuracy how elements behave and combine. This is one of the most remarkable achievements of modern science. Protons have a positive electrical charge, electrons have a negative electrical charge, and neutrons have no charge. True or false? Atoms are the smallest units of matter. True or false? There are different types of atoms with different numbers of protons, electrons, and neutrons. They are called. Every element has an atomic number determined by the number of neutrons found in the nucleus. True or false? When atoms have fewer or more neutrons than protons, they are called. The atomic mass of an atom is the total mass of all its protons, electrons, and neutrons. True or false? When an atom loses or gains 1 or more electrons, it is called an. The properties of an element depend on the behavior of its electrons. True or false? Electrons with a given energy follow certain patterns around the nucleus. These are called atomic. The first quantum number describes the spin of an electron. True or false?